The economics of strategic behavior is impacted by different types of information, imperfect or asymmetric, and thus our economic toolkit needs ways to discuss information. First up, we'll consider symmetric information, but symmetric and imperfect information. We'll consider situations where no one person has a special information advantage over someone else, but we are not certain about which of the outcomes our actions will lead to. Thus, we'll start by looking at the actions of individuals once risk, uncertainty, and imperfect information come into play. We'll need probability theory to distinguish what happens when we act when under uncertainty. We will consider what happens to economics when information has limits, everything is not necessarily known, and choice is more nuanced. In the world of imperfect information, probability theory is going to help us out greatly. There's more to say in an uncertain world than simply, I don't know, or I do know. A subjective probability is simply a degree of a belief that a person assigns to a certain proposition. Beliefs can range from the impossible, p equals 0, to the certain, p equals 1. Whenever we think of a certain situation, the sum of all probabilities of an event must be equal to 1. The main objection to using subjective probability theory is the objection of realism. People state that no one really goes around assigning probabilities to every event that they see as a possible likely outcome of their actions. Even so, people almost always have some probabilities in the back of their minds. Just because you do not know everything with certainty does not mean you have no clue about things. Perhaps you can assign a reasonable guess probability. Thus, probability theory can help us model individual rational choice. We can think of this as decision theory. We can talk about probability theory, and we can use it to discuss choice under uncertainty. So we're going to use this idea of simple probability theory to make these decisions, or to think about making these decisions, when we do not have perfect information. First up is going to be expected value maximization. How do we think about people choosing between gambles, between choices that don't have certainty? In particular, what is the relationship between the value they put on having some outcome X with certainty, probability equals 1, versus having some outcome X with a probability of less than 1? The simplest theory we can use is expected value maximization. It's pretty easy to do, and so let's go with this because a lot of what we can do in information economics is in comparison to this simple model of expected value maximization. So, with expected value maximization, all we do is simply kind of follow the math. We multiply our outcomes by the probabilities that they happen, add them together, and we see what our expected value is. So with this example here, we're going to be indifferent between the following two options, option A and option B. Option B has certainty. It's $10.99 with a probability of 1. But option A is a type of a gamble. We're not sure as to what's going to happen with this outcome. With a 1% chance, we will end up with $1,000, and with a 99% chance, we will end up with $1. Expected value maximization states that these two outcomes will end up being exactly the same. Why? Well, option B is easy. It's worth $10.99. Option A, what do? We just take our outcome, multiply it by the probability, and add it to the other outcomes multiplied by their probabilities. So we take $1,000, multiply it by the probability of 0.01, and that's worth $10 to us. And then we take $1, multiply it by a probability of 0.99, and that's worth 99 cents to us. And so what we end up with is we get a situation where option A is worth $10.99. Option B is as well. Let's take this approach, let's take this tool and walk through a famous thought experiment here. The thought experiment is called the St. Petersburg Paradox. This is a game of chance for a single player in which a fair coin is tossed at each stage. The pot starts at $1 and is doubled every time a head appears. The first time a tail appears, the game ends and the player wins whatever is in the pot. When a tail comes up, it does not mean that you have now lost and you're out of the game. It just means that your run is over. How much would you be willing to play this game? Think about that for a minute. Right? How much would you be willing to play? The pot starts at $1. Anytime that a head comes up, if you flip a coin, the pot's going to double. So if a head comes up once, you get $2 now. If a head comes up twice before a tails, you get $4. If a head comes up 3 times before a tail, you get $8, and so on and so on and so on. No matter what, you get whatever's in the pot once a tail comes up. How much are you willing to pay to play this game? How much is it worth to you? Well, let's think about it with the simple tool that we have so far. What is the expected value of this game? The expected value of this game is infinite, because there's always a chance that a head will come up next and come up next and come up next. And so we can't really calculate it. It's going to be this infinite amount of money that you could potentially get. And so this proposes a little bit of a dilemma here, a little bit of a paradox, because my guess is when I asked you how much would you be willing to play this game, you did not think to yourself somewhere around an infinite amount of money. Right? Most people look at this and they might say, oh, I might pay like $2 or $3 to play this game. So within economics, we can use the tool of expected value maximization, but does it really make sense to use when it can't handle such a simple paradox as the St. Petersburg Paradox here? Expected value maximization is highly tractable, but it's also highly unsatisfactory. Would anyone really prefer $1,001,001 at a probability of 0.001 to $1 million for sure? I think I would take the $1 million for sure. So something's up here with our expected value maximization. Is economics left without answer? Well, the way out is expected utility theory. So we can think of expected utility theory as acknowledging the idea of diminishing marginal utility. Daniel Bernoulli in the 1700s dealt with the St. Petersburg Paradox. They looked at the mathematical expectation as being infinite. So we thought about, well, how do you assign value then? How do people evaluate risky situations? And the hypothesis is this idea that's very similar to an expected utility hypothesis. People maximize the expected utility, not the expected value. And a utility function of wealth is often represented as not linear. As the curve increases, the slope declines, and thus the expectation of the utility of wealth is less than infinite. This brings to the table marginal utility and diminishing marginal utility. The modern application of this kind of idea is the von Neumann-Morgenstern idea of expected utility. Expected utility theory's intuition is that instead of maximizing average wealth, let us suppose that people maximize expected utility. And the key insight is that expected values of the outcomes do not need to have the same rankings as the expected utilities. Expected values are useful as a reference towards our expected utilities, but we're going to move beyond expected value and move into this world of calculating expected utility to try and model how individuals actually act under uncertainty. All right, so for our von Neumann-Morgenstern expected utility, we have a 3-step procedure. First, what we're going to do is we're going to assign a utility to the potential payoffs. Look at each payoff and analyze the utility that would come if we got that payoff. Next, what we're going to do is we're going to take that utility and weigh it according to the probability that that payoff will happen. So at step 1, we say, okay, if we got this payoff, how much is it worth given our utility function? And then at step 2, we take that end result from that one payoff and we multiply it by its probability. At step 2, we do this for all of the potential payoffs that we could have from the gamble that come out of step 1. And then step 3 is quite easy. We choose whatever gamble has the highest weighted outcome. All right, so here's a numerical example for us to consider. Imagine that we're given a utility function of the income that we have is to the 1/2 power, or the square root of our income. That's our utility function. And we have 2 gambles to consider. Option 1 is a 50% chance at $10,000 and a 50% chance at $0. Option 2 is $3,000 with certainty. Which do you choose? Well, let's go through our three-step procedure here, right? So given that we have this utility function, and we look at option 1, we're going to assign a utility to the potential payoffs. Then we're going to weigh the outcomes according to their probability, and we're going to choose, finally, whatever gamble has the highest weighted outcome. So with option 1, we say, all right, we have a 50% chance at 10,000 and a 50% chance at 0. So we want to take the first payoff, the $10,000, and say, how much utility would that give us if it came up? And so what we do is we take that and we say, okay, we find the utility that we would get from having the $10,000. And then we find the utility that we would get if we got the other payoff, the $0. And what we do is we plug that into the utility function. And then we take each of those answers and we do step 2. We multiply it by the probability of it happening. Right? So now what we end up with is the expected utility from those two potential payoffs within that one gamble. Well, this one works out quite easily because we have a 0 figure over here. So this is all going to 0 out. All of our expected utility is going to come from the first part of our equation. And what we end up with is an expected utility of 50. So for option 1, we have an expected utility of 50. But now let's consider option 2. So now in looking at option 2, what we have to do is the same three-step procedure. We're given the same utility function that we had before. Remember, what we're doing is we're trying to say, for this individual with this utility function, which of these two options, which of these two gambles will result in more utility? So what we do is we take the step 1, we take this payoff and we plug it into our utility function, and then we multiply that by the probability that this outcome happens. Well, in this case, it's the only outcome. It's happening with certainty, so the math gets pretty easy here. We simply plug the payoff into our utility function here, and then we multiply that by the probability of 1. And so what we end up with is an expected utility of 54.8 in this situation. So what we got in this example is an expected utility of 50 for option 1 and an expected utility of 54.8 for option 2. So our third step of our process is to simply choose the higher expected utility option. So in this case, we choose option 2. One thing you can do to follow up on this is think about if your answer would have changed if you were just doing expected value calculations. And it turns out your decision would change. So see if you can prove this to yourself. Give you another example here, example 2. Now we have a different utility function here. So now we can see that our utility is our income squared that we get from this payoff. In option 1, we have a 5% chance of $1,000, and in option plus a 95% chance of $0. But in option 2, we have $200 with certainty. Which one of these two do you choose? See if you can do the math following the same process. What you're going to do is you're going to take this $1,000, plug it into your utility function, then multiply it by its probability. You're going to take this $0, multiply or put it into the utility function, multiply it by the probability. You're going to end up with a 0 out over here. And then you're going to take this $200. You're going to plug it into your utility function, and you're going to multiply it by 1 because it's happening with certainty. And then you're going to compare those outcomes. From example 2, what you should get as your answer is that option 1 gives you an expected utility of 50,000. Option 2 gives you an expected utility of 40,000. And so you should choose option 1. We can use the same basic structure of calculating expected utility to calculate certainty equivalence. We can use this math to work through and think about how valuable gambles are to us. We call this the certainty equivalent. What certain level of income gives me the same utility as the utility from some gamble? The easiest way to think about this is to actually go through and solve these out. Once you see the certainty equivalent math, it starts to make more sense what this actually means. But the basic idea is that you're looking for some certain level of income that gives you the same amount of utility that you would get from some gamble, right? So let's look at the process for doing a certainty equivalent. So first up, what you're going to have to do is find the expected utility. So you're going to find the expected utility from some gamble, and then what you're going to do after that is you're going to take that expected utility and you're going to plug it back into your utility function and solve for the amount of wealth or the income that you would have when the probability is 1, when we have that outcome with certainty. So really what we're doing is we're kind of reversing the equation here. We now know at step 2 what the utility should be. We're trying to have it be equivalent to the utility that we get from the gamble. We know the probability from this situation is a probability of 1. There's not multiple options that we can have because we're trying to say what amount of wealth when we have certainty gives us this amount of utility. Right? And so what we're doing is we're moving back into the equation and trying to figure out what the payoff from this gamble, of having a probability of 1 would have to be to give us the same utility that we got from a gamble. So here's a big list of potential certainty equivalent calculations that we can do, and we'll run through some of them. So this list of payoff comes from Brian Kaplan's notes on information economics, and what it's asked to do is to come up with the certainty equivalents for 3 different gambles with 3 different utility functions. So we're going to look at the first gamble, this gamble 1, and we're going to look at it with a certain utility function, and we will fill in the chart that corresponds to that. But then we will also look at, say, gamble 3 here, and with a different utility function, and we would fill in the chart here. And so what we'll do is we'll run through a couple of these examples with gambles 1, 2, and 3 at different utility functions, but then you can fill in the rest, and I'll give you the answers within this video to see if you understand how to calculate the certainty equivalents. So let's move to this next example of figuring out certainty equivalents. So imagine gamble 1. The expected utility that we have to find, that's kind of our first step here, is we have to look at gamble 1 where we have this 50% payoff of $100 and a 50% payoff of 0. We have to take those payoffs, multiply them into the utility function. We're going to do the utility function of the square root of x, or x to the 1/2 power. And then what you do once you plug them into the utility function is you multiply them by the corresponding probabilities, add them together, and you get the expected utility. And so here we have an expected utility of 5. But when we're doing the certainty equivalent, we don't stop there. What we do is we say, okay, well, what certain level of x gives us an expected utility of 5? So now we know the expected utility of the gamble is 5. So we're going to say, what level of income with certainty would give us this same expected utility? So now we know the utility is 5, and we know our probability is 1 because we're trying to say this amount of x with certainty, and we know the utility function. So what we can do is we can say, all right, well, the expected utility is 5, the probability is 1. We don't know what amount of income, but we do know the utility function is to the 1/2 power. And so simply draw this up, and now we have one variable left. And so we need to solve for x. When you do the math, we get an x of 25. So the certainty equivalent for a gamble of 50% of 100 or 50% of 0, when your utility function is x to the 1/2 power, is 25 as the payoff. And so that becomes our certainty equivalent for example 1 here, or for gamble 1 here. So let's look at another gamble here. Let's look at gamble 1, but let's look at it with a different utility function. So let's look at gamble 1, but now let's look at it with the expected utility of just x. So look at gamble 1, but now with this new utility function. No longer is it x to the 1/2 power, it's just simply x. So what do we get? We have to plug in our 100 multiplied into the utility function, which it's just x. So we just have that 100 there. We have that 0 into its utility function, so we just have 0 there. Multiply it by its probability, multiply this by its probability, and we end up with an expected utility of 50. Then what we can do, now that we have the expected utility, when we're trying to do the certainty equivalent, is we can do our second step of finding the certainty equivalent. We take this expected utility from the gamble and plug it back into our equation with an unknown x, but a probability of 1 and a known utility function of just x. And what we end up with is 50 equals x. 50 equals x times 1 to no power here, no changes, it's just x. And so what we end up with is x equals 50. And so the certainty equivalent for gamble 1 with the expected utility function being just x is 50. And now let's do one last one here. Well, let's do gamble 1, and let's look at it with the x squared utility function. So again, you simply find the expected utility. In this case, it'll be 5,000. And then to get the certainty equivalent, you take that expected utility and plug it back into the equation. So you say, hey, the utility has to be 5,000. We don't know what x is. We do know what the utility function is. It's whatever x is squared. And then we also know what the probability is. The probability is 1. So you can take all of this second part here if you want and times it by 1. But that's just going to leave you with this x squared. And then you can simply do the math from here, and your x will be 70.71. And so that becomes your certainty equivalent for gamble 1 when your utility function is x squared. Right? And so that means that this certain level of money, 70.71, would be equivalent to the gamble. Right? They would view it the same as taking the gamble. It provides the same amount of utility when we have 70.71 with certainty as this particular gamble. So it's the certainty equivalent for that payoff. All right, here's the rest of the chart filled in. So if you want to go through and kind of test yourself on gambles 2 and 3 to find the certainty equivalents, you can do so. Certainty equivalents are very useful for thinking about the behavior of individuals, in particular, their behavior when confronted with risk. Remember, certainty equivalents are what certain level of income gives me the same level of utility as the utility from a particular gamble. When the expected value is greater than the certainty equivalent, we can say that you have risk aversion. Risk aversion is the reluctance of a person to select a payoff that bears a higher estimated rate of return because it also has a higher rate of uncertainty. With risk aversion, you value the certainty and are averse to the gamble, right? And so here we have the expected value should be greater than the certainty equivalent. You would be a person who has risk aversion. You value the certainty and you're averse to having the element of gamble from the payoff. But sometimes we aren't necessarily risk averse. Sometimes we could be risk neutral. You're indifferent between a gamble and a guaranteed payoff as long as the expected values remain the same. When the expected value is equal to the certainty equivalent, you have risk neutrality. Other times we can see individuals as acting with a risk-seeking behavior, looking for a gamble as opposed to a guaranteed return when the expected values are the same. You're risk-seeking. You value the risk. You're seeking the gamble. You're seeking the gamble or the chance at the big payout. So we have 3 different ways of thinking about how individuals could act, and individuals might act differently in different situations. So sometimes I might be risk averse, and in other times I might be risk seeking, but we can model individuals with these 3 ideas, and we can relate the certainty equivalents to the expected values. One way that we do that is what's called the risk premium. This is the compensation an individual would require to bear risk without suffering a loss in expected utility. When the expected values are the same, how much would I pay to have a non-gamble over the gamble? If you're, say, risk averse in this situation. The maximum amount that you would pay if the expected values are the same to have the non-gamble over the gamble would be your risk premium. To find the risk premium, we will need the difference between the expected value and the certainty equivalent. The risk premium must be positive if we're risk averse, though you can calculate the risk premium for those who are risk seeking, but in that case, the risk premium would just be negative. So let's look at the 4-step process to calculating the risk premium. Imagine that you are given a gamble. So in this case, we're going to say you have a 50% chance at 100 and a 50% chance at 0. And you're given a utility function, in this case, the square root of x. What you do for your 4-step process for the risk premium calculation is first you find the expected value of the gamble. So in this case, what we do is we just simply multiply 0.5 times 100 and 0.5 times 0, and our expected value is 50. Now what you do at step 2 is you find the expected utility of the gamble. And so what we have to do for the expected utility is take each payoff and multiply it in, right, to the probability. So take 0 into 50 with the utility function, right, given the utility function. So what we have is we plug that 100 into the utility function, 0 into that utility function, and then multiply it by those probabilities, right? So just like what we were doing before to find the expected utility, and in this case, the expected utility is 5. Step 3 for figuring out the risk premium is you need to find the certainty equivalent. So now we take that expected utility from the gamble of 5 equal to 1 with certainty times an unknown amount x within the utility function that we're given, x to the 1/2 power. And we do the math and we figure out the certainty equivalent in this case is 25. Well, what you can see so far is in this calculation of a risk premium, we have had to do everything that we've done up to this point in this lecture. We've calculated the expected value, we've calculated the expected utility, we've calculated the certainty equivalent. The last and final step for calculating the risk premium is, at step 4, you take the expected value and you subtract from it the certainty equivalent. So in this case, the expected value was 50, and the certainty equivalent that we received was 25. And so our risk premium is going to be 50 minus 25, or in this case, it will be 25. And that will conclude the economics of information introduction that we've given here, where we think about making decisions when we do not have perfect information, when uncertainty exists, and using the basic probability model of the von Neumann-Morgenstern approach.